All right, I hope everybody is refreshed and ready for the last talk in this session. Aljosa Peperko from the University of Ljubljana will end the session with some results on positive kernel operators and Banach function spaces. And yes, feel free to start.
Janko, thank you very much. Can you hear me well and see the screen?
Yes.
Okay.
Everything works.
Karim, also thank you very much for giving such a tough talk that is hard to follow. Okay, so I'll speak about some results on positive kernel operators. So the topic will be topics, depending on the time, will be from, let's say, 3 papers. So two of them already almost published. So the first one was published on logarithmic convexity positivity. Yes. And the second one here below has just been accepted. And the third one is still preprint. The talk will be of 2 parts. So let's first speak about logarithmic convexity for some stochastic kernel operators. So perhaps some introductory definitions or remarks. Probably most of it wouldn't be necessary, but still okay. Let mu be a sigma finite positive measure on a sigma algebra, and let m plus denote the cone of all equivalent classes of almost everywhere equal mean measurable functions with values from 0 to infinity. And let us use, I will use the following notation. So by f positive, I will note this will mean that the set of all x's such that f of x is positive has positive measure. And by f strictly positive, I will mean that f of x is strictly positive for almost all x from measure space. Okay, by M0, I don't know what is, I think is usually denoted by L0, so the vector lattice of all equivalent classes of almost every equal complex mean measurable function on X. Okay, and I will speak about ideals, so probably it's not necessary to repeat what an ideal is. So also, I think this the definition of wedge is quite standard, but I will still repeat what I mean here by a wedge. So a wedge is a subset of L if it contains sums of functions from C and multiples of it, multiples with positive numbers. And as usually, X is called the carrier of L if there is no subset of positive measure with property that f would be 0 almost error on y for all f and L. So, and I will assume that here throughout that x is the measure space is the carrier of the ideal. So an operator is called the kernel operator if it has a kernel, right? And if it holds that this is finite, this is finite, and that is, and it can be written in such a way for all f and L. So a kernel operator is positive if and only if its kernel is non-negative almost everywhere, because we assume that x is the carrier of L. So by a substochastic kernel operator, I mean that the positive kernel operator is a substochastic if the following holds. So if we looked at only matrices, this would mean what column substochastic matrices, right? And the operator is stochastic if this integral over all x's is equal to 1 for almost all y and x. Good. So we will consider the following wedge. So if we have a substochastic kernel operator S on L, let us define the set C of S as the set of all strictly positive functions from L, such that there exists a stochastic operator L that dominates S, and that F is a fixed point of A. So this cone appeared in some work of Sahi and his co-authors. And in the next result, I will present some infinite dimensional generalization of some of their results. So the finite dimensional version of this result, so for matrices, appeared in Sahi in 1993, but was already contained in earlier work by Sahi and Yao. This result was a very important step in the proof of existence of Nash equilibria in some model of exchange economy with complete markets. The generalization that appeared in the first one of the first paper that I mentioned before is the following. So let L included in L1 be an ideal, and assume that S is a substochastic kernel operator on L, which is not a stochastic operator, and let alpha be non-negative numbers such that its sum equals 1. Then it holds that C of S, as we defined before, so let me perhaps repeat what C of S is. These are all strictly positive functions such that there exists a stochastic operator L that dominates S, and that A of F is F. So C of S under these conditions is exactly this. So all strictly positive functions from L such that S of F is less or equal to F. And consequently, C of S is also a wedge, and consequently, C of S is a logarithmic convex set. So this means that each that for any F1, F2, Fm from C of S, its weighted geometric mean is also in C of S, and this is the property that Sahi and his co-authors used mainly in the proofs. And consequently from 1 and 3, also the following property follows, so that this holds for any lattice semi-norm on L. So the first inequality follows from 1 and 3, and the last from some generalized Hölder's inequality, right? Okay, so perhaps let's take a look a little bit at the proof. So one inclusion is trivial, right? So we need to show that, so let F be strictly positive. And so we need to prove that F is in C of S if and only if S of F is less or equal to F. So in one direction, it's clear if F is in this set, then since F is a fixed point of A, there exists some stochastic operator, and since F is equal to FF, this is more or equal to SF. So this inclusion is clear. So the converse is less trivial, but the proof didn't need some special technique. It could be directly generalized from Sahi's results, but one needed to be careful under what conditions it will hold. So let's assume that S of F is less or equal to F, and define phi to be F minus SF. So this is in L plus. And if we denote T as we did before, so the integral of over axis of S of the kernel of S, then let psi be 1 minus T. For all, so we define it for almost all y, right? And let lambda be this integral, and by assumption, since this psi is strictly positive on the set of positive measure, this means that this is a positive number, and it's finite number. It is a finite number because f is L1. Okay, and let's now define a suitable stochastic operator L, so kernel operator L that dominates S, and it has a fixed point equal to F. This is what we want, so we define it like this. So let the kernel A be equal to S plus 1 divided by lambda, and then multiplied by these two functions, phi and psi. Okay, so then it is not difficult to verify these things, that A is a measurable function that satisfies this condition that we need, since we have these properties here. And then one can also verify that we have that A of f is equal to f. This goes directly from definition, right? Because if we integrate here, this guy here is lambda, right? So it cancels out, and phi was just f minus sf, so this is direct. So this is true. So, and then by Fubini theorem, we can also calculate that lambda is exactly this integral of phi dx. So it follows, what we need to show is that this integral, that this kernel operator is stochastic, right? So because of this, we have that this integral, by using a definition, it is equal to 1. Here we used this fact that this integrates to 1. And so we have established what we wanted. And consequently, it follows directly from this description that COSAEF is also a wedge, and also that it follows directly from this description that it is a logarithmic convex set, because if we have such a weighted geometric mean, then by Hölder's inequality you have this, and then this quickly follows. So, okay, perhaps some remarks are in order. I won't go into too much detail. I'm not really a specialist on the subject, but so what was the role of this theorem, like say in finite dimensions, in the theory of strategic market games? So, Sahi and Ya described an exchange economy with complete markets and proved the general theorem for the existence of active Nash equilibria. So what they showed is that under replication of traders, this equilibria approach the competitive equilibria of the economy. And the model that they looked at was first proposed, this model was proposed by Shapley, and it represents one of the two possible generalizations, let's say, of single money model, but considered previously by Dubé and Shubik. So, and what was this wedge C of S? In the finite dimensions, their wedge here corresponds to the set of all possible positive multiples of price vectors that arise as some trader alpha varies his bid in his strategic set, where trader alpha is the only trader with unfixed bids. And so then they combined this version of this finite dimensional version with suitable Kakutani fixed point theorem to show that there exists Nash equilibria. So one would expect here that this setting, that this exchange economy can be generalized to infinite dimensions, and probably combined with suitable fixed point theorem, and this result that I presented here should prove what we would like. But I didn't go into details here, so if somebody would be interested in this topic for further research, feel free to contact me or do it yourself. I'll be more happy to see the results. So Okay, so this is where I finished with the part one. So I think I'm somewhere on the halfway. So in the second part, I will speak about some inequalities on kernel operators, which are with results that are a bit more recent. So here I will, in some of the results, I will look at just sequence spaces, and in some of the results, I will look at Banach function spaces. So what I will say, what a Banach sequence space is, this is just a Banach function space over the set R, where R is, it can be a finite set or the set of natural numbers when equipped with counting measure, right? So Banach sequence space is just a Banach function space over this simple measure space. And I will usually assume that Banach function space is from this collection of L. So, and this is the collection of Banach sequence spaces such that the standard vectors are in the Banach function space and that they have norm 1. And on this assumption, also this R is then the carrier of L. By R of K, I will know the spectral radius of an operator. I will consider only linear operators here, although I like to consider also nonlinear operators, but here I will speak about linear operators. The RS will be the essential radius of K. So the spectral radius of the Kalkin image of K in the Kalkin algebra. Okay, so in the case of sequence spaces, I will just look at non-negative matrices under a suitable space, and they will define in this special case positive, since they are non-negative, positive kernel operators, right? So let K1 to Kn be non-negative matrices, alpha as before, and let us denote this non-negative matrix. Let this non-negative matrix C in such a way. So on the diagonal, we just take the convex combination, the generalized convex combination of this. So the arithmetic mean of the diagonal elements of K, and of the diagonal, I take the weighted geometric mean of the elements. So here I will present some generalization of result of Cohen in approximately when I was born. So Cohen proved that the spectral radius of n by n non-negative matrix is a convex function of the diagonal elements. He proves a bit, I think, a bit more so on he did need that the diagonal was non-negative, but so he proved this result, and a few years later, Kato provided quite nice generalization to the setting of Banach order spaces and in the setting of strongly continuous semigroups of operators and their generators. But there, in his proof, he needed quite a lot of the theorem, these strongly continuous semigroups. But later, we, together with my former supervisor, Roman Drnovšek, we considered this this problem for, let's say, infinite matrices, and we got direct proof without using Kato results. In fact, if I'm completely honest, I didn't really go to all the checking all the details if this result would follow from Kato, because the proof itself was more direct. The proof itself was more direct, and it didn't need any result on strongly continuous semigroup. But when doing this, then one can go back to Kato and try to perhaps prove some additional results there. So perhaps this is a good way to one way of research, because these are nice results of Kato. So what we considered with Roman was the following. So if L is a Banach sequence space and such that from set L, and let K1 to Kn be non-negative matrices that define operators on L and alpha as before. Okay, I will present here, I will denote here rho is again in this setting again the spectral radius, but later on it will be also something else. So I will write this theorem like this. So for the spectral radius, we have the following. So that the spectral radius of this matrix C, as I defined it before, this matrix was defined in finite dimensions, I think, perhaps by Elsner and his co-authors for the first time. I'm not sure, but I think I found it there. So is less or equal to the arithmetic weighted arithmetic mean of the spectral radii. So in particular, if K1 to Kn have the same non-diagonal part, right? So that means that all diagonal they are the same. Then this follows because of the definition, of the matrix C, right? Then we just get this because of on the diagonal you just have something like this, and off the diagonal then we assume here that we have the same non-diagonal part, and this holds. So in other words, this means that if D1, Dn, so sorry for the intrusion, sometimes some telephones ring, so we'll need to let it go. So in other words, if D1 and Dn are diagonal matrices, and K is such a matrix such that K plus D1 to K plus Dn are non-negative, and that they define operators on L, we have this convexity, right? We have this convexity. So this means that the spectral radius is convex, considered as a function of diagonal also in this setting. So this result, we proved this with Roman quite a long time ago. I think 2010 it was published. But okay, recently I noticed that if we assume that, if we additionally assume that L and L star, so L and its dual, have ordered continuous norms. So for example, for L piece, where P is strictly between 1 and infinity, so then the above inequalities hold also for the essential radius, right? So this can be proved, and a very similar proof works in both cases. Okay, I won't go into details of the proof, but I will speak about some ingredients of it. So what is needed in the proof, let's say. So again, let K1 to Kn now be positive kernel operators with kernels. So and alpha as before. And so then the Hadamard weighted geometric mean is defined as a kernel operator with the kernel which has weighted mean of kernels as its kernel. And it is, if L is ideal, then this is a well-defined operator on L because of this well-known inequality, right? So, and in the proof, you need this, in the proof of the previous theorem, you need this theorem that was done earlier. So again, under the above assumption, so we assume here that L is Banach function space, and that K1 to Kn are positive kernel operators. You have that this inequality holds if for the operator norm, this means here the operator norm, and for the spectral radius. It also holds, let's say, on L2, it holds also for numerical radius. And if in addition L and L star have ordered continuous norms, then this inequality holds also for the essential radius and for, let's say, a suitable measure of standard measure of non-compactness also. So in the case of matrices, of infinite matrices, you can prove a bit more. So if you have alpha such that its sum is less or equal to 1, then this inequality still holds for the spectral radius and for the operator norm. So it does not hold, let's say, under this assumption for numerical radius. This can be shown. But for the essential radius, I'm not, at the moment, I don't know if I'm completely honest. I tried a few things, how to prove it. I must say I didn't really look for a counterexample. So for me, it's still not completely clear if this inequality under assumption that L and L star have order continuous nor under, and if we have here a non-negative matrices, infinite matrices, and we assume that the sum is more or equal to one, I don't know if this holds also for essential radius of Nash or not. I didn't really go to look for counterexamples. I must admit this. So if somebody has an answer to this, I'll be grateful. Perhaps I still have few minutes to mention this. Okay, so in the last two papers that I mentioned, I considered also this symmetrization of a kernel operator. So if K, let us look now at kernel operators on L2, and then let K be a positive kernel operator, and let Sk denote the symmetrization of it. So it means the kernel operator with kernel equal to the geometric mean of the kernel, right? So you can write it like this: Sk is equal as the weighted geometric mean of K, and it's a joint. Okay. Okay, we can consider a weighted version of this by putting here K to alpha and here the joint of 1 minus alpha. So this is an operator with this kernel. So perhaps here weighted symmetrization is not a good name. If somebody would suggest some other better name, please do. So this here is a Sk is a self-adjoint operator. Here it may not be, but if you put alpha is equal to 1/2, then this is then a generalization of this one, right? And perhaps since I'm getting close to out of time, I perhaps mention this, perhaps the most interesting result here. This was theorem 6, was proved by Roman Denoshek for, let's say, in the case of symmetrization. So in the case of when alpha is 1/2. And in the case of the spectral radius, but then I noticed that it can also be proved for the essential radius and slightly generalize it. It goes like this. So let us denote, let rho be or spectral radius or essential radius. So since we are on L2, the assumptions are okay, as similar to the previous results. So then denote rho n as the rho, so the radius or the essential radius of this operator S alpha to the K to 2 power n, and then also take the root of it, the 2n root of it. And then the following inequalities hold. So this was known that this rho S alpha is less or equal to rho of K. This was known before, but then we have the following chain of inequalities. And here is a quick proof. Perhaps I won't even, you can read it yourself. I really won't go into it. So first you prove this, you can prove it directly if this was, it follows directly from 9, let's say, that is written up here. Or you can prove it directly, since also you can dominate operators here. And then the rest follows from the result that I mentioned earlier. And this inequality in between can quickly be seen that they follow directly from this inequality 10. And so let me perhaps stop here. So thank you for your attention.
All right, thank you very much for your presentation. Are there any questions you want to ask? Okay, I would say there are no questions. Everyone's happy. That's also nice. And thanks again for your nice talk, Aljosa Peperko. And also thanks for all the other speakers for this session. This means now that we come to an end for this session and we have an hour break. I really enjoyed it, and I'm also looking forward to the next session. And I hope everyone is going to have a nice break, whether you have lunch, dinner, breakfast, or whatever, wherever you are right now. And yes, I see you all later.
Okay, bye-bye. Thank you. Thank you, Thank you to the chairman also.
Thanks. It was my pleasure.